Hello, my name is Kunle, and I'm the co-founder and chief technologist of Samba Nova Systems. And the title of my talk today is Accelerating Software 2.0 for IoT and the Edge. As we know, there's been a huge proliferation of IoT devices. The projection is 64 billion IoT devices by 2025. There are a range of different things that you can do with IoT. You can have cameras for security and for monitoring traffic. You can have sensors for civil built infrastructure. You have for power lines, for roads, for bridges. And all of these devices generate a lot of data that needs to be collected, mined, and interpreted to make better decisions, right? And so typically this is done using, today, using models, using AI models to interpret the IO data, which necessarily means using machine learning. So machine learning is a new way of developing applications, and the widespread use of machine learning in the form of neural networks and deep learning has the potential to fundamentally change the way that we develop software. So if you think about traditional ways of developing software, often called software 1.0, the code is written using some sort of high-level language like C++ or Java, and the process of developing the software is to start with a problem, decompose the problem into a set of components, devise algorithms for those components, and then build the components back into a system. Contrast that with software 2.0, which was coined by Andrej Karpathy, or the term was coined by Andrej Karpathy, and here the idea is that the programmer input is training data. And the goal is to generate the weights of the neural network by some sort of learning algorithm. And of course, doing this means that the training data will determine the sets of models that get generated. So the use of software 2.0 has been, and machine learning has been used to solve a number of hard problems, such as language translation, image recognition, medical images, images from cameras and images on the web, and also robot control. As an example of the benefits of software 2.0, Google shrank its code for language translation from 500,000 lines of imperative code to 500 lines of data flow. And by doing this, of course, you got a number of benefits, right? So that you got, of course, fewer lines of code to actually write, but other also benefits in the deployment. The new models could be deployed with fewer amounts of memory and in a ways that were more predictable runtime. And so the goal of Samba Nova Systems is to develop the next generation of systems for software 2.0. My co-founders are the CEO, Rodrigo Lian, who's had a long career managing huge hardware projects, both at Sun and Oracle, and is an expert in VLSI design. And my other co-founder is Chris Ray, who is a professor at Stanford and is well known in the fields of machine learning and databases, and is also a certified MacArthur Genius. And so thinking about how to develop systems for software 2.0, two computing trends, the whole notion of developing these systems is driven by two computing trends. The first is the fact that multi-core approaches to computer design are running out of steam. It doesn't matter whether these cores are large cores, as you typically get with Intel or AMD processors, or more streamlined high throughput cores, as you might see in a GPU. Fundamentally, the cores are inefficient, and putting multiple cores together means that you have even more inefficiency. And so what we need, especially at the point of time that we're now in with Moore's law the improvements of Moore's law declining, we need architectures that are fundamentally more efficient. So the other big trend is the convergence of training and inference, right? So typically today, the types of accelerators used for machine learning training are different from the sorts of computation environments that you use to run inference. And by bringing them together, you get a lot of benefits. So these two computing trends are driving the design of the next generation of systems for machine learning and software 2.0. As I said, software 2.0 is all about data flow. And the way that you describe algorithms and applications in software 2.0 is by using these high-level frameworks that machine learning application developers use, like PyTorch and TensorFlow. And these fundamentally produce a data flow graph that represents your application. And the elements of the data flow graph are the core kernels of the machine learning algorithms, such as convolutions and matrix multiplies and norm batch normalization kernels. It turns out that you can take these data flow graphs from machine learning applications and convert them into a form that is better for high performance execution. This we call parallel patterns. And parallel patterns can be thought of as a high-level representation of both the computation and the data access patterns in your algorithms. And we've seen that you can take these parallel patterns and optimize them for higher computational efficiency. So what we have done in SambaNova is take this fundamental execution mode of called parallel patterns and cast and accelerate it in hardware. So we've got a native way of executing parallel patterns in hardware using what we call a reconfigurable data flow architecture. So the reconfigurable data flow architecture is composed of both compute units called pattern compute units and memory units called pattern memory units. And these can be composed together with an on-chip dynamic network to support the computation and data flow requirements of the particular machine learning application. So as an example of how this looks, you can look at the data flow representation that I showed earlier, and I show it mapped spatially onto an array of reconfigurable computational memory units that would exist inside the SambaNova chip. And this provides very efficient computation and very high bandwidth communication between the different kernel elements. And all of the communication stays on chip and is supported by the on-chip network. And so when you're thinking about designing a high performance system, there are two key things that you've got to balance: computation and communication in order to get high performance. And traditional architectures like CPU and GPUs allow you to program the computation, but they don't really allow you to program the communication, the data flow. But by using a reconfigurable data flow architecture that supports both of these elements of high performance computation efficiently, we can get improvements in both performance and flexibility, and we can make possible the sorts of applications that were not possible before. We call these kinds of transitions 0 to 1 applications. You weren't able to do it with the conventional architecture, the conventional computational infrastructure, but with SambaNova, you can. So today, if you look at the machine learning pipeline, what you see is different platforms, software and hardware platforms, being used for training and inference. Typically training, both training from scratch that we call de novo training, and training in which you repurpose an existing model, is done with GPUs because you use large batches of data that are efficiently processed by GPUs. But inference, because you only are inferencing one example at a time, this doesn't work very efficiently on GPUs, and so you typically do this using a CPU. And so what has to happen is you've got to revalidate the model that you train on a GPU and in order to run it on the CPU. And furthermore, you don't have the ability to modify the model by retraining on the CPU because the CPU does not support training very efficiently. So this sort of difference between training and inference is particularly a problem if you want to continuously do IoT stream processing. So this is something that I'm doing at Stanford University with my colleagues Kayvon Fatalian and Chris Ray. And what you want to do here is, given a stream of data from some IoT device like a camera, you want to continuously adapt your model to better model and interpret the data that's being sensed by the device, right? So the data is changing, and also potentially you want to change the decisions that you're making, and you want to continuously adapt, right? So as an example, let's look at what might happen in an environment in which you have a camera, right? So if you look at the traditional ways of doing camera processing, you start with images on the internet, images of cats and dogs and all sorts of other things. And your goal is to come up with a set of models that give you high classification accuracy among a large number of categories. But contrast that with a situation where you've got some IoT camera probably monitoring an intersection somewhere in the country. But here you're likely to see all kinds of vehicles, trucks and cars and maybe motorcycles, but you're unlikely to see a giraffe. You're not likely to see a lion. And so there are lots of things that you won't see. But what you will see is a shift in the type of images that you see on the camera, right? So here's an example looking at an intersection, and you've got different weather conditions, right? Sometimes it's dry pavement, sometimes there's rain, sometimes there's snow, sometimes there are people walking around. And so you get different sets of images, and you need to be able to have a model that can deal with this so-called distribution shift, right? So weather, time of day, types of vehicles, etc. And so, a good example of where you see this would, of course, be with intersections where you get this different sets of data, and you need models that are capable of dealing with that. And so the solution that potentially works very well is this idea of continuous model adaption, right? So here you're trying to take very tiny, efficient models that can retain high accuracy for complex tasks, but you're going to continuously adapt them to specialize to the contents of the video streams. So the way to think about this is that you don't want to worry about coming up with a model that can handle everything, all situations that you might actually see. And that's sort of course, we would require a training set that covers all the situations that the camera might potentially see. What you want to do is to have a model that can quickly adapt to the scene and the data at hand. So as an example task, let's look at semantic segmentation, where you're trying to detect people or animals or objects and distinguish or segment that object from the background, right? So you see a lot of examples here of people, animals, or cars, and then being distinguished from their background. Okay, and so the way to do that using this continuous adaptation model is a just-in-time model, right? And so the idea is you come up with a small model, a deep neural network that can be evaluated and trained quickly, and then you have a much larger model that you train with a huge amount of training examples. We're going to call this the teacher model. So you've got a teacher model that knows a lot of things about how to model a large, very complex scene, and you've got a much simpler student model. And the idea is that periodically you retrain the the student model using recent data, and you use the teacher model as the supervision, which tells you how well the student model is doing. So let's look at an example of how this works in segmenting some table tennis players in a tournament, right? And so you see on the left here, we have the teacher model, which is this regional convolutional neural network. And then on the right, we have this just-in-time network, which is this much smaller model, which is periodically retrained using information from the teacher model. And you see that basically they track. There are times when the woman walked over to the judge where things didn't track as closely. But if you look on both sides, you see that fundamentally the segmentation is working just as well on the right as it is on the left. Okay, and so you see, so this approach really does work, and what you get is a tremendous improvement in performance, right? A 20x improvement in performance, and this includes the time that it takes to do the periodic retraining. So what are the implications of this continuous adaptation? Well, so the key thing that it does is it places these extra demands on the deployment platform, right? So you need the flexibility to execute inference very efficiently, and you need to be able to do the training online. So anything that, any accelerator that only does training or efficiently, but doesn't do inference very efficiently, won't work in this environment. Also, you need to be able to handle the small student model efficiently, and also the large teacher model, and run that efficiently. So a accelerator GPU that can run the large teacher model very efficiently, but can't run the student model very efficiently, won't work well in this instance. And then you also have to have the capability of being able to dynamically move between one model where you are doing inference and another where you're doing training, and be able to do that in real time and decide when you need to do to run the teacher in order to do the supervision. So SambaNova, with its ability to do large batch training very efficiently and small batch or single instance inference, gives you this capability. So what we can do is this convergence of training from data center to the edge, right? So in the data center, you can train the large model, and you can train the large model from scratch. You can deal with huge amounts of data. You can get very efficient training, and you can build models with very high accuracy. And then you can deploy this model with lightweight, continuous adaptive models like JITNet, and you can continuously retrain the model to take advantage of the specific environment, and to adapt to the data that is coming from the IoT device, such as the saw with the camera input. And so, to conclude, then, you know, SambaNova Systems is in line and supports these two computing trends. It provides a much more efficient computational structure substrate for doing both inference and training, and is much more efficient than conventional architectures. And it supports this convergence that allows you to implement the sorts of capabilities that are required for the future of IoT and edge model development and computational requirements. So thank you.